Okay, welcome back. We're working our way through Module 2, which is all about georeferencing. Last time I spent a lot of time talking about distortion, and that's one of the key things you need to know about georeferencing, is because when you model this 3D object as a 2D map, you're going to be distorting either shapes, areas, distances, or direction, and you need to kind of know what you're distorting so that your map, as realistically as possible, depicts the thing you think is most important. Before I continue with georeferencing, I kind of need to talk a little bit about scale. Now, most of you think about scale like the rest of the world thinks about scale. Some people call it geographic scale. So something that's a large scale project will cover a large area. Something that's a small scale project will cover a small area. But there's this other understanding of the word scale, and that's what's called a map scale. So map scale is different from a geographic scale. A map scale is a ratio. So a map scale is the ratio of the distance on the map, so let's say 1 inch on my map, divided by the actual distance on the Earth. So if 1 inch on my map represents 1 mile on my map, the ratio would be 1 over 5,280 times 12, whatever that number is, probably somewhere around 10,000. So map scale is a ratio of the distance on the map divided by the distance on the Earth. So this is an example of a legend or a title block for a satellite image map, and you can see that it tells you what the scale is. 1 unit on the map is equivalent to 2 million units on the surface of the planet. So that would be the map scale, 1 to 2 million. There's also another way of representing the scale using what's called a scale bar. So now you can imagine that this scale bar was on a map that was, say, 8.5 by 11 inches. And then for some reason you zoomed into that map and you made the map much bigger. Well, the scale bar would get much bigger. But would the ratio get bigger? So you need to kind of keep in mind about map scale and how to depict map scale in terms of if it's an electronic map or if it's a printed map. If you're going to use a printed map, you want to make sure that you have a scale bar so that when you zoom in to things, the printed version of that zoomed in will zoom in also, and the scale bar size will move. Notice also here there's some other georeferencing stuff. This is telling me that it's a Lambert conformal conic projection. So we know conic means it was projected using a cone as a developable surface. Conformal means its distortion in terms of shape is minimal. And standard parallels, there's two of them, one at 26 degrees and one at 34 degrees. That means that the cone is cutting into the surface of the planet so that those tangents to the surface of the planet cut through at 26 and 34 degrees north latitude. Also see that this thing is called the Everest spheroid. Everyone should remember that a spheroid is an ellipsoid, which is the smooth model that we use to depict our planet. I didn't talk about an Everest spheroid, so this map is telling you that it uses an Everest spheroid, which has associated centers, semi-major and semi-minor axes. Okay, so when you make a map, the scale that's on the map is only going to be true at that point where your developable surface is cutting across the surface of your planet. So in this case I have a Mercator, which is a cylindrical projection, and it's oriented so that the equator is the standard parallel. So along the equator of my map, 1 unit might equals 100,000 units. But since we know that this cylindrical projection tends to distort things away from the standard parallel, it's going to distort things so much that at the south end of the map, the scale factor is actually 2. So 1 unit up here is 100,000 ground units, 1 unit down here is, or 100 million ground units, 1 unit down here is 50 million ground units. So the scale has gone in half or doubled by scale. So there's a lot of distortion in there, and if you try to measure something on a map, if you measure something away from where that scale factor is 1 at the standard parallel, you're going to be getting incorrect numbers. Here's another topographic map. This is a 7.5 minute, which means it covers 7.5 minutes. And if I look in the title block of this, I see that it's for Snow Flat Cave, Provisional Edition, 1989. And I look a little further and it shows me that the scale is 1 to 24,000. So this is the standard scale for USGS topo maps at the 7.5 minute map size. So 1 unit on the map is equivalent to 24,000 units on the Earth. And again, you can see their scale bars here, so you'll be able to use the scale bar if it zooms up or zooms down with your printed version. And it's also going to tell you something that we'll start talking about next week that has to do with data and data standards. And this is telling you that the map complies with a certain set of standards, and that's going to tell you how accurate the data are on the map. Okay, so you remember this from an earlier video. Locally, it's not a big deal. You can see things. It's easy to measure things. We just define the surface, and everything's good to go. But we need to select a projection if we're going to go anything larger than just locally. And so selecting a projection becomes kind of a two-step process. The step that you first need to consider is what the scale of your map is going to be, the geographic scale. How much area is your map going to cover? And so this comes from your text, and you can see that there are different scales up here at the top. Large scale is a large ratio. So this is map scale. So a large scale map is going to cover a smaller area. A small scale map is going to cover a larger area. So this goes from covering a small area to covering larger and larger areas all the way out to where you're covering the world. So depending upon what the scale of your map is going to be, you're going to want to pick a projection that is designed to minimize distortion over that scale. So if we look at some of the more common projections, a transverse Mercator projection is one of the most common ones we use in the United States, at least the contiguous United States. And you can see that a transverse Mercator projection is going to be good for all the way from a map covering small areas, which is a large map scale, to a continent. Okay, so it's going to cover a large range of scales, which is good. The other one that gets used frequently is a conic projection called Lambert conformal, and you can see conformal, that means it's going to try to minimize distortion of shape, and again it's going to cover a large range of map scales from small area to large area. So those are two of the more common projections used for the lower 48 United States. But you got to remember distortion, right? Some projections are good at preserving one property or another, and others are not so good at that. So when we look at the ones that we're going to be using for the United States, we see that the transverse Mercator is good for conformal mapping, which means it's going to make the shapes look like they do on the surface of the Earth. Likewise with the Lambert conformal conic, good for shapes, but notice that neither one of these are good for areas. So if your map is going to involve areas, like say you're doing something that involves calculation of states and the population in a state or something like that, you may want to use a projection that's going to minimize distortion in area so that the map is actually showing you the proper size of the features that you're looking at, as opposed to just the proper shape. So you need to pick a projection that's going to fit not only your scale, but the aspect of reality that's most important to you. So here's a couple common projections. Lambert conformal conic. So we've got conic projection. Conformal means preserving shape. And we've got universal transverse Mercator. So Mercator is a cylindrical projection. Transverse is like a cylinder that's rotated down so that it's laying on its side. So the transverse Mercator projection is a cylindrical projection where the cylinder is, the axis of the cylinder is oriented east-west. There's another set of systems called state plane systems, and I'll talk a little bit about those. Those are the kind of things that individual states use for their own mapping purposes, because that's going to minimize distortion over the surface of their state. So it's more scale customized for their state. And then in the next video I'll talk a little bit about public land survey systems. That's not actually a projection, but it's a method for describing land parcels that's been used in the United States since the Revolutionary War, that gets used a lot frequently, so you'll need to kind of know how that works too. Okay, Lambert conformal conic. There it is down here. You can see it covers a large range of things. So in our case, it's going to be good for a continent all the way down to a small area. It's going to fit for what we want it in the United States. This is what a Lambert conformal conic looks like for an entire hemisphere. And if you remember from the previous slide, Lambert conformal conic isn't going to really work for a hemisphere. Anything above about a continent, it's not going to work very well for. And you can see that that's obvious here because you've got a lot of distortion if you include too large an area. And this would be where the standard parallels are on that conformal conic. So you're going to have minimal distortion where those standard parallels are. In this case, Lambert is at 33 and 45, so that would be somewhere in the south central and the north central United States. We're going to have zero distortion, and we're going to have minimal distortion between those points. And east-west, we're going to have not really that much variation in distortion. So it kind of depends upon which topographic series you use, which standard parallels there are, but these are the ones that are going to apply in our area. Here's a graphic that shows this universal transverse Mercator projection. That's a cylinder laid on its side, and in this case you can see that where it's touching the planet goes right through that longitude. And what universal transverse Mercator does is it allows this cylinder to rotate around the Earth to make different projections who have a tangent at different longitudes. So since this is where it's touching, distortion is going to be minimum around that point. If you wanted to have something that had distortion minimum over here, you might pick one that's rotated just enough so that this line applies over here. This is a link to a website out at Penn State that animates this, and it kind of shows you how the rotation of the cylinder works and how the projections work. This is a depiction of how the grid that's associated with this transverse Mercator projection works. There are zones, and each zone is 6 degrees of longitude wide. So each one of these vertical lines is 6 degrees away from the adjacent line. So the area between these lines is one zone. The north-south rows have to do with where you're going to choose the origin of your coordinate system so that the projection works out as well as it can, and so that the numbers associated with the projection are the easiest to put into your GIS. This zooms in a little bit, and you can see there are several zones shown here. So for example, zone 17 has a central meridian. This is where there's no distortion at 81 degrees east longitude. So this is the way that looks. This thing has 6 degrees of width at the equator. Remember how longitude lines curve in so that they meet at the poles. So the zone actually scrunches down, another technical term, as you get closer and closer to the poles. So the origin of the projection itself is at the equator, which is 0 degrees north. Depending upon which zone you're at, you will have different coordinate starting points because it starts at the central meridian of that zone. This shows the entire United States, or the contiguous United States, and you can see that in Idaho we're actually straddling 2 different zones, and that causes problems, and I'll talk about that a little bit in a minute. But if somebody in western Idaho is using UTM 11 and they give their data to somebody in eastern Idaho that's using UTM 12, that's going to be different because they're going to have different origins and they're going to have different central meridians. So there needs to be a process, if possible, that can combine both east and western sides of the state into one coordinate system so you don't have to deal with data crossing coordinate systems. Here's another depiction of UTM. In this case it's zone 11. And zone 11N is the N grid, so if you moved up from the equator you would get up to that N grid. This is where the origin is. They actually falsely move the origin away from the central meridian to the west so that all the numbers of any locations inside of this zone are positive. They have a positive X coordinate. So that's what that's called. That's called a false easting. So everything is falsely given a number that's larger than it would be if it were measured from this point. False northing would be if you were to move the origin of your system north. Okay, so that's the universal transverse Mercator. You can rotate it around, go to the entire planet, cover a nice area with low distortion. There's another system called the state plane coordinate systems, and you can see that the states break up their coordinate systems into different pieces or different regions depending upon the state. And in general, states that are oriented east-west will use one coordinate system. States that are oriented north-south will use a different coordinate system. So the two common coordinate systems I've talked about, one of them will be used for east-west states and one of them will be used for north-south states. If we look locally, we see that Montana decided they're not going to have anything but Montana coordinate systems. Washington has a north and a south. Idaho has a west, a center, and an east. And if we look down here, we see that there are things here that say NAD 27 and NAD 83. Those are datums which reflect which ellipsoid was used to create these coordinate systems. So NAD 1927 uses that old ellipse, the Clark 1860 or whatever that ellipse was. The NAD 1983 uses the newer ellipse that was developed using satellites that had an Earth-centered ellipsoid. So way back in the early videos we talked about ellipsoids. These are going to distinguish between two ellipsoids. That too will become important when you're changing coordinate systems because you have to apply what's called a transformation if you go from one ellipsoid to another ellipsoid. And 27 and 83 use different ellipsoids, so you need to apply a transformation to move from one to the other. This is a screenshot from ArcGIS, the GIS system that you're using, and this one shows state plane Idaho west, and this is in feet. It's using the NAD 1983 datum, which is going to pick a certain ellipsoid. And if you look down here, you can see that there's a false easting. It's moved the origin over to the west. There's no false northing. Tells you where the central meridian is. So this isn't one of those universal transverse Mercator meridians. This is a special meridian that's defined for this coordinate system. And that's what makes that different from UTM. It's transverse Mercator, but it has a different central meridian and it has a different latitude of origin. So your coordinates will be different between that and the regular UTM coordinate system. Here's one for Washington. Washington, remember, has a north and a south. Washington, since it has a north and a south, it's not going to use that transverse Mercator. It's going to use Lambert conformal conic because this one's better for east-west trending zones. So Lambert conformal conic for east-west, transverse Mercator for north-south. Your state plane systems are going to use different projections depending upon the orientation of the zone. Idaho has come up with yet another projection that they use for the data that are developed by the state of Idaho, and that's called the Idaho Transverse Mercator System. And what that does is it says we're not going to deal with having multiple systems for our single state. We're going to divide it. We're going to devise a single coordinate system that applies to all of our state. That's the Idaho Transverse Mercator System. There's a website where you can look at the details of what that projection involves and why they chose that right there. When I talked about some of projections using certain ellipsoids and other projections using different ellipsoids, if you're trying to mesh data between two different excuse me, ellipsoids, you need to apply a transformation. And and the transformation that you'll apply will depend upon which ellipsoids you're going from. So if you're going from 27 to 83, you might use a certain transformation. If you're going from 83 to WGS 84, you might use a different transformation. So you need to kind of know what this is doing. The GIS maybe will try to do it for you automatically, but it probably won't do as good a job if you're doing anything that's kind of custom or special. So next time I'm going to talk about the public land survey system. That doesn't involve a projection, but it involves a way of specifying land that's used throughout the United States, especially public lands. So you need to know how that works. And I'll see you next time.